This conference will now be recorded.
Let my screen come, then we'll start. Okay, so we'll conclude this chapter, dual nature of radiation and matter, by discussing Davison-Germer's experiment and taking a few numerical examples. So on this chapter, dual nature, like all the way from photoelectric effect and this de-Broglie's hypothesis. So in the last class, we had discussed de-Broglie's hypothesis. What was that? The de-Broglie's hypothesis was that if radiation, that is the photon or the light or any electromagnetic radiation, can act as both particle and wave, so which we have seen in case of photoelectric effect, that light behaves as discrete particle. Okay, discrete particle, which are called discrete entities, which are called photons. Okay, which are called photons. So that we have seen. Then de Broglie comes up with the reverse idea, that if radiation can act in both way, like wave, it has dual nature, wave and particle, then any material particle which is in motion can have conversely some wave nature, and the wavelength of that kind of particle, any material particle or matter, will be given by lambda is equal to h by p. This is the de Broglie's equation or de Broglie's hypothesis, whatever you say. P is the linear momentum. So material particle in motion can also behave behave as wave. Okay, so this lambda sometimes denoted as lambda d, to denote the de Broglie wavelength. And this wave actually is not electromagnetic wave. This is called matter wave. Okay, so you might be thinking why I'm just repeating this again, because we need to know why this experiment was being done. See, in 1927, Davison and Germer designed an experiment to prove this hypothesis. I had already told what is called hypothesis in the previous class. Actually, hypothesis, like based on some arguments, some logical facts, you can give some idea, some theory, okay, or some thoughts. So that can be told as hypothesis unless and until it is proved by some experimental some experiment in some laboratory by someone. It is not going to be established as theory. So de Broglie's hypothesis was being actually tested by many scientists in many laboratories, but these people, Davison-Germer and another set of people, G.P. Thomson, okay, G.P. Thomson, they had actually proved that yes, material particle in motion can behave as wave. Okay, so this is the thing we are going to prove today. So look, how we can prove wave nature of anything. We have seen in the optics, wave optics, that diffraction phenomenon can be explained only by wave nature of the light, isn't it? So if something is actually showing diffraction, some entity like I have, see, I'm telling that electron is a material particle, proton is a material particle, neutron is material particle, even I can take alpha particle, beta particle, whatever. So these are material particles. That means they have finite momentum. Particle nature is characterized by momentum, and wave nature is characterized by wavelength. So this these are physical entities or particles which has momentum. But we have to show, if we want to prove de-Broglie's hypothesis, then we have to show that this material particle, electrons, they have de-Broglie wavelength, some wavelength. That means electrons are behaving as a wave, protons are behaving as wave, neutron may behave as wave. So those things you have to prove. So Davison and Germer, they wanted to prove that electron in motion can behave as wave. So what they have done, they had actually designed an experiment for electron diffraction to study the electron diffraction. Electron diffraction means what? So you have seen that diffraction of light you have seen. So that's where we could explain the diffraction property, diffraction by wave nature. So if some, see, if electrons can exhibit diffraction phenomena under some condition, then we can say that electron has wave nature. That's all. So this Davison and Germer in 1927 they have designed an experiment where they could evidence electron diffraction. Electron diffraction. So now I'll explain you the experimental arrangement how they had done this experiment. See, for diffraction to happen, wavelength has to be nearly equal to the slit width or less than that. Okay, or less than that. So this is what the condition we had seen. So when electrons are in motion, they have very small wavelength compared to any wavelength we are knowing. So it will be actually very less wavelength, something like of the order of 1.5 or 6 angstrom, etc. Okay, less, this much small wavelength will be there for electron. So see what Davison and Germer had designed to like evidence this electron diffraction experiment. See, they have taken one electron gun. You can see this is the shape of a gun, right? This is called electron gun. You can see this. It is already written over here. So this is called electron gun. What is this electron gun? Actually, electron gun has a filament. You can see just like incandescent bulb, they have filaments. They glow light, right? They actually becomes very hot and then they glow. They radiate light, isn't it? Similarly, if you take a suitable metal and then heat that metal filament, then at sufficiently high temperature, this metal filament will emit electron. What they will do? So it will emit electrons. Okay, electron will be emitted from this filament. Now, if you look here, so we are just studying electron diffraction. Electron diffraction. Sorry, by mistake I have just removed this electron diffraction. So this is electron gun which can produce electrons. Okay, so this is called filament. So this is denoted by F. Filament actually emits electron upon heating. Okay, and see, this is called anode. This filament actually act as cathode. See, and this is a hollow tube kind of that. Okay, this is actually known as, this is actually anode. So this cathode, between cathode and anode, there is a suitable potential applied through this high tension. You look here. This is, so this is the potential divider. Yeah, circuit. You can just change, or maybe this you can say as rheostat. You can change the potential difference between this filament and this anode. Okay, so filament act as cathode, okay, which can emit electron upon heating, and this tube is actually called anode, and between this cathode and anode very high potential is or suitable potential will be applied such that electrons from here will be accelerated towards this side. Okay, will be applying, say negative potential is being given in the cathode, so electrons will be actually accelerated. Okay, electron will be accelerated. Now what you can do is this electron, accelerated electrons, if you just make a nice collimated beam of out of it, so fine beam light, light beam, you can understand, right? Similarly, you can have many electrons, a bunch of electrons. So when you collimate them like a ray, then it will be called as like composed of ray. So it will be called as beam of electron, fine beam of electron. So fine beam of electron will be actually directed to a crystal here. This is nickel crystal. This is nickel crystal. This is called target. So you are just bombarding electrons to the surface of this nickel. Why? See, the structure of nickel is shown here. Inner structure, structure of nickel crystal. Nickel crystal. So any crystal, any crystal has definite arrangements of atoms inside it, as you can see from here. Definite arrangements, very periodic arrangements are there. Look here, this is, and these arrangements, see, these arrangements can be thought of one plane. See, these atoms all together can form a plane. So this is plane 1. Okay, this is a plane. Another set of atoms which are arranged in a regular manner. So this is plane 2. Like that, in a small, even small crystal, there will be a, like there will be a suitable arrangements of the atoms, and we can actually consider, or we can think that they are forming a planes. Either you can think planes in this way, or otherwise planes are already shown, you can see that. So you can just consider that there are parallel planes of, like planes, parallel planes. Look, these are the parallel planes just joining the atoms. Okay, these are parallel planes. So these planes actually will act as mirror. You might be thinking, what is this? Okay, so look here, when the electrons are hitting the crystal, they will be actually scattered by the atoms in the planes of this crystal. Okay, see, you have, see, planes, this planes, it has 3 electrons, here 4 electrons. Like that, there are electrons in each plane. And see, electrons are not haphazard, they have certain arrangement. See, this distance is called atomic, interatomic distance. The distance between two atoms is called interatomic distance. It is denoted by small a. Interatomic distance, you will be learning in your higher classes. Interatomic distance. Okay, and when you find out interplanar distance, distance between like consecutive planes, that is denoted by d, that is denoted by small d, and that small d is actually called as interplanar spacing. As you can see here, interplanar spacing in this case, look here, interplanar spacing is this d, the spacing between the two plane. So this is written over here. Okay, so what will happen, see, this gap between two electron, okay, this gap will act as slit width. Okay, this will act as a slit, this will act as a slit, like in case of Young's double slit experiment. Even in case of, like when you see diffraction pattern, diffraction experiment. So what we have seen, we have seen that there is a source of lights, and then you have a have gap between them. So this will act as actually slit. Okay, and when electrons are coming and hitting the crystal, those electrons will be actually reflected or scattered by the atoms you see in these planes. Here, this figure is representing that, see, the electron, incident electron, see like this is electron, incident electron going up to here, hitting and coming back. This is called scattered ray. It is kind of reflection, Bragg reflection. This is called Bragg reflection. Okay, scientist Bragg had done this kind of he had given a theory on that. So Bragg's relation, Bragg diffraction condition, we'll see. So see, incident, this is called incident ray, okay, which is making an angle theta with the planes. So this is the angle which is called glancing angle. This theta is called glancing angle, okay, and this is also glancing angle. And see, if you think just like a mirror reflection, see the incident ray is coming and getting reflected, okay, and you look this angle of incidence, if you think this as in incidence angle, this is alpha, so angle of reflection also will be alpha. So in fact, these are two rays which are called, one is called incident beam of electron, and this is scattered by atoms on the plane of these crystals. Okay, so this is reflected or scattered, you can say scattered scattered electrons. Okay, scattered electrons. So this is the thing. See, this scattering is itself called diffraction by crystal. Okay, so nickel crystal has been used as like grating, diffraction grating. The planes in this actually will act as diffraction grating. And see, whatever electron comes, it will be scattered by these various planes, various, not only one plane, it will be scattered by various planes of this crystal. Okay, various planes of the crystal. And when, see, this crystal can be rotated, see, this crystal can be rotated about an axis which is perpendicular to the plane of the nickel crystal, okay, on plane of the paper. So when you rotate, see, the incident electron beam will be scattered in different directions. In different directions it will be scattered. Okay, so incident electron beams or electrons will be scattered in different directions. Okay, now see what you have. This is called movable collector of electron, or this is called detector also. You have to see, we don't know where electron cannot be seen, so you have to detect the electrons after scattering. So this is incident electron which is hitting the nickel crystal, and then it is actually getting scattered or diffracted. Those diffracted or scattered electron can be detected by detector. Okay, this is called movable collector of electron. So this is movable, why? Because if you rotate your crystal, the electron beam now at this angle it is scattered. Sometime it will be scattered by this angle. Okay, sometime maybe this angle. Okay, so it can scatter with respect to incident ray. It can scatter in different angle. Okay, different angle it can scatter. So you have to collect all the electrons. Okay, like electrons scattered in different directions. So if you sometime collect sometime here, if you collect sometime, okay, sometime here, again sometime here, so then you can see at which angle, like at each angle electrons are there or not, first of all. So and also you can find out in each angle how many electrons are also collected. See, if you collect electron here, maybe some 50 electrons, some angle maybe you can collect some 30 electrons, somewhere you may collect even 100 electrons. So that variation also can be seen. Okay, so what has been done, in this experiment, these scattered electrons are collected at different angle with respect to phi. So what is this angle? Phi is a scattered angle. This is called angle of scattering. This phi Okay, so this phi is called angle of scattering. What is the angle? Angle of scattering. Angle of scattering. Angle of scattering. What is that? This is the angle between the incident beam of electron and diffracted beam of electron. So angle between incident and diffracted beam of electron. This is called phi angle, angle phi, or scattered angle, or scattering angle of scattering. So with respect to this angle, you can plot the number of electrons. Okay, number of electrons. So you cannot find directly the number of electrons. So in this detector, there will be some scintillation counter or something like that. So which will actually, or Geiger-Müller counter, whatever. So there you can find out. See, this is there is a galvanometer to here. What what to do? Actually, see, electrons collected here will be reacting with some chemicals or something. So it will actually convert that electron will actually give rise to equivalent amount of current. Okay, so that current can be plotted with the angle. So that current is actually directly equal to the number of electron. Okay, number of electron. Okay, so this is how the intensity of the diffracted electron beam has been plotted against the scattering angle. Not only that, every time this anode potential has been changed. Suppose, see, I'll show you what has been done. The experimental result. See, this is the experimental result. Experimental result. So experimental result. What was that result? See, upon scattering, whatever and whatever electrons were collected at different scattering angle, so that was plotted. So this is actually the intensity. This is actually intensity, or the number of electrons, you can say, which is directly related to this intensity, was plotted against various angle of scattering, and at the same time, not only scattering angle. So this has been a plot, like this is actually plotted for only accelerating potential 40, then 44 applied accelerating potential has been made 44, then the accelerating potential has been made 48, and thus it went up to 68 accelerating potential. And you look what they have observed, what they have observed. As you grow the accelerating potential, there was no peak here, no peak. Now as you increase the accelerating potential, peak arises. Okay, peak arises, some peak arises. Now as you increase further, it is increasing. Okay, this peak intensity, so peak intensity is increasing. And it was seen that it is becoming maximum. It is becoming maximum at 54 accelerating potential. This peak is becoming maximum. And what was the angle of this peak? This angle of peak in the sense, it was this one. Okay, scattering angle, this is phi. So this scattering angle has been, see, at scattering angle. So what was the thing? At scattering angle, phi is equal to 50 degree, and 54 volt applied accelerating potential. There is a maximum peak intensity. Okay, this is what was observed. See, in this is for nickel crystal. Okay, so you can change the nickel to some other crystal also, and then do the same experiment, and then you can prove that. So we'll see. So this is the significant result you have got, and after that the intensity, peak intensity decreases. Okay, the experiment was carried out for various other accelerating potential, but it is seen that at 68 accelerating potential, the peak actually vanishes. Okay, so what was the conclusion from here? Actually, the conclusion is that the maximum peak intensity obtained in a particular direction is due to constructive interference of electrons scattered from different layers of regularly spaced atom. What is that? See, it is because of the diffraction you are getting the peak, that is sure. What is diffraction? Actually, diffraction is also superposition of waves only or interference only. So you look here, I'll clean everything. See, there are planes here, planes here, planes here. So there are whole lot of planes. So some electron beam which is actually scattered in this direction. If from some other plane also it is scattered and meet here, they will superpose and they will, if they constructively interfere, they will give maximum intensity which was seen at scattering angle phi is equal to 50 degree. So that is what has been seen, and this is happening due to diffraction. Okay, this is happening due to diffraction. Okay, and look, if we, so you might be thinking that that means, see, that means what is happening, electron is actually behaving as wave, electron is behaving as wave, and at particular this frequency, sorry, this particular accelerating potential 44 volt, the wavelength, de-Broglie wavelength is becoming suitable for exhibiting maximum diffraction. Okay, maximum diffraction. So what we can do is actually we can calculate, see, experiment from this experiment we know, like there is Bragg's law of electron diffraction. What was that? You can find 2d sine theta is equal to lambda, n lambda. This is for nth order diffraction pattern. Okay, for nth order diffraction maxima, nth order diffraction maxima will occur at this condition, 2d sine theta is equal to n lambda. Now if we find for, if we just find for n is equal to 1, that is for first order diffraction pattern, first order diffraction maxima, this, then from here you look, I know the d is the interplanar spacing for nickel crystal, this I know as 9.14 angstrom. Okay, 0.9 0.914 angstrom. Okay, and then 2 anyway, and theta, from the experiment we have seen that maximum intensity has been seen at, oh, okay, this is not theta, actually theta is actually this one, glancing angle, as I showed in the beginning. Okay, maybe, yeah, I'll show in the you in the yeah, later time. See, this glancing angle is theta. Okay, according to Bragg's law, 2d sine theta is equal to n lambda. This theta is actually glancing angle. The angle the incident electron beam is making with the planes. Okay, that is called glancing angle. Okay, so this angle actually 20 so 65. How do you get? So if this is 50, so it is actually 1. See, this is 90 minus 25. So 90 minus 25 will give you 65. So this is theta. Maybe let me go there and show you. So this glancing angle we had been taking as theta, right? This is glancing angle. Now we have seen 2 alpha is 50 degree. Okay, 50. And see, this is also theta. The angle made by scattered ray with the plane. Okay, so if this is theta, so 2 theta plus 2 alpha will be is equal to 180 degree, and 2 alpha is actually 50 degree. So if you do this, you will get, okay, so, oh sorry, 0, this will be 130. So theta will be actually actually 65 degree. So 65 degree this theta is. Okay, now if we put this 2d, d is this one in angstrom, and theta as 65 degree, then if we do the calculation, see lambda will be 2 into 0.9.14 angstrom, and this is sine 65 degree. So you will get actually something like 1.65 angstrom wavelength from this Bragg condition. Okay, Bragg condition for diffraction, electron diffraction in crystal, nickel crystal. Okay, so we can find out the wavelength from this diffraction experiment. This is called electron diffraction experiment. And see, still we can, so this is wavelength, one way of getting wavelength from diffraction pattern or diffraction experiment. Now if we do, see, we know the accelerating potential is 54, where we see this maximum intensity. Now if we want to find out the de Broglie wavelength at that particular potential, so if you accelerate an electron with V potential, EV will be kinetic energy equal to P square by 2m. So this we have already seen, that P will be then root over 2m into mass electron of mass V. So if you just put this in this de Broglie's expression or equation, 2me into V, then mass of this along with 2 and this h will give you a nice factor, that is 1 point, oh sorry, 12.27 or 1.27, sorry, 12.27 or 12.3 divided by root over capital V. This V, if this is in volt, then you will get the wavelength in angstrom. I'll write in the next page maybe. So what we have learned in the previous day, on the previous day, that if an electron is accelerated by certain accelerating potential, then the the de Broglie's wavelength can be calculated using this formula, h by under root 2m into ev. So what is, so if we just put the value of m, mass of the electron, e, charge of the electron, and this is Planck constant, then and this is in volt, then you can get that 12.3 divided by capital V in volt. V is the applied voltage or accelerating voltage. Okay, if you keep this in volt, whatever you get will be in angstrom unit. Now see, we have got 54 volt, right? 54 volt. So if we put this in here, plug this here, 54 volt, it is actually approximately will be obtaining 1.66 angstrom. So in the previous case, what we have seen from this uh, electron diffraction, this Davison and Germer, they have found out the wavelength as 1.65, and directly using the de Broglie's hypothesis. This is called de Broglie's hypothesis. Broglie's hypothesis using, okay, so hypothesis, we can write this and put the value of mass of the electron, E is the charge of the electron, and this is the voltage given, that is 44 volt. Okay, where we see the maximum intensity for a peak. So if you use this in volt, you will get this 1.66 angstrom. So from the experiment we get 1.65, and from directly using directly using de Broglie's hypothesis, we get 1.66. So these are actually in agreement. That means your experimental value and your theoretical value using de Broglie's hypothesis, they're matching. They're matching each other. That means what? What we can conclude is that electron must be behaving as a wave having wavelength nearly equal to 1.66 6 angstrom at that particular experiment. Okay, so this is how it was proved that from this experiment is called electron diffraction experiment, and by doing this electron diffraction experiment, Davison-Germer and later GP and Thomson, they proved the the existence of the wave nature of electron, and thereby the trueness or or the or the validity of de-Broglie's hypothesis. They have proved the validity of de-Broglie's hypothesis that any material particle in motion will also exhibit wave nature. Okay, so this is what we have seen from this experiment. So this is whole about the experiment. So now, as I promised, I'll do one thing. I'll take up few numerical examples for today, uh, to overview the whole chapter. Basically, I'll take up few examples from this de Broglie hypothesis as well as photoelectric effect. Okay, so I have few MCQ type questions. So Deepa, I hope you are able to see this. If you can answer, I'll be very happy. Or shall I discuss and you will be listening today, and then later on you will try. Shall I just discuss the questions? Okay. So what I do, I'll read out the question and I'll pause for 1 minute and see if you can answer for this question. If you have answer, you tell me. If you don't have, then I'll just explain you how to do that and what will be the possible answer. Okay. See this question. First question is, according to Einstein's photoelectric equation, the plot between kinetic energy of emitted electron and incident, like for frequency of the incident radiation. So this is photoelectric effect. I'll just give you some hint that, see, there is a photocathode. Okay, there is a photocathode, and you are actually irradiating or illuminating this with some incident photon having energy h nu. Okay, this photocathode, and then electrons will be emitted from this. This is called photoelectric effect. This we know. And from Einstein's equation, what is Einstein's equation? We know Einstein's equation is actually the kinetic energy, maximum kinetic energy is equal to h nu, that is the incident photon, energy of the incident photon minus work function. Okay, W0. So this is the expression, or this is the Einstein's equation for photoelectric effect. Now you have to say from this equation which one of these four curves will be the correct one. Which one of these fours? Like yeah, which one of these will be correct? So this is plotted against frequency of incident photon and the maximum kinetic energy of the emitted electron. So look here, in this experiment you can see that there will be a case when you won't have any kinetic energy. Okay, case in the sense, see, you should have a minimum frequency okay, below which below which this kinetic energy is zero. Actually, from here also, this Einstein's equation, like Einstein's equations of photoelectric effect, from this equation you can infer this. Okay, so where it is showing out of these four curves. See, there are kinetic energy 0 for two curves. One is this one, another one is this one. Here also kinetic energy is starting from 0. Otherwise, kinetic energy is not starting from 0. Here also kinetic energy not, at least we don't see here in the curve, in the range of this frequency, that there is 0. Okay, so these two, see which one is saying that unless you reach a certain minimum frequency which called threshold frequency. Here you have to remember threshold frequency. Okay, threshold frequency means you are just giving a light on the photo sensitive material, but all frequency of incident light will not be able to make any photoelectric effect, okay, or make electron to come out. Only when there is a minimum frequency applied, that is called threshold frequency. And see, out of all these ports, this graph is showing you that there is a threshold frequency, okay, for the process. So this is the threshold frequency nu 0, nu 0. Okay, so this C, curve C will be the answer. Okay, otherwise there is no threshold frequency here. There is threshold frequency 0, it is not possible. There is no, here is also no threshold frequency, etc. Okay, now let us go to the next problem. This is a numerical problem. You have to do some calculations. If the threshold frequency of a metal used for photoelectric effect corresponding to wavelength 5000 angstrom, then how much is the work function? See, here also you have to use the Einstein's equation. So see, they have told you that this is the threshold frequency. Okay, then how much is the work function? Actually, work function, see, I'll tell you from this equation itself. So Einstein's equation says kinetic energy maximum, kinetic energy of the emitted electron will be h nu minus w0. H nu is the energy of the incident photon, and this is the work function. Now, what will be the work function means what? You know, when the energy of the incident photon is becoming greater or equals to work function, then only you will be able to see photoelectric effect. Okay, as long as this is not happening, your incident energy is at least not becoming equal to work function, you are not going to see any photoelectric effect. So in this case you have to use this concept, that so how much work function for the metal. So if this much energy, this much like if the radiation having this much radiation wavelength exhibits photoelectric effect, that means, see, this wavelength corresponding to this wavelength, whatever energy you have, that energy will be equal to, must be equal to this work function. So I can write, so if I know for a photon, so for a photon energy is h nu, so let me tell you, so this work function will be equal to the energy of the incident photon. So this nu can be converted, like just replaced by, see, from this relation, nu lambda is equal to c, so lambda will be is equal to, sorry, nu will be is equal to c by lambda. So if we use this hc by lambda, hc by lambda, okay, so this will be the energy of the given photon. Now look here, uh, hc by lambda, there is also a nice, uh, actually nice simplified calculation. hc by lambda, if your lambda is actually in nanometer, okay, then, okay, so look, what we know is hc, actually this will be 1 to nanometer. Okay, so this will give you actually this kind of, this is joule Yeah, so if you just put the value of this and this, you will get this is electron volt and nanometer. Okay, this will be 12,400. So this is a factor actually. So this is this much nanometer, and if you make this as nanometer, angstrom as nanometer, or here directly, since the answers are given in this way, don't go to the electron volt and all. We can directly put the value of this hc by lambda. We can directly plot the value of c, h, etc. So hc by lambda, because these are given in joule itself. So see, this joule, this h is actually 6.63 into 10 to the power minus 34 joule second, and this is 3 into 10 to the power 8 meter. Okay, and divided by, this is 5000 angstrom, 10 to the power minus 10 meter. If you just do this calculation, then you must be getting the answer. Okay, so you can do this calculation, Deepa, by yourself. So look, this will come as something like 3.998, and see, we can just take this. This is 3, so this will be 7. 10 to the power minus 7 plus, so it is actually minus 34 plus, this is 7 and 15, so it will be around 4 into 10 to the power minus 19, 19 joule. Okay, so this will be the answer. Okay, so what you have to do, hc by lambda, whatever wavelength was given, you have to make hc by lambda, then you will get the work function for that metal. Now actually I have got some another 5 minutes. I'll just discuss at least few more, two more, or yeah, few more questions. So following figures shows the variation of photocurrent with anode potential for radiation of three different frequencies. Which of the following statement is correct? See, you have got photocurrent in this axis, you have got anode potential. You know, you might be remembering that this was the cathode and this was the anode or collector plate, and see, photon was hitting this cathode, electrons were emitted, and there was a potential given across this these two plates. Okay, cathode and anode. So electrons will be accelerated and collected by this anode plate, like that it was. So the photocurrent depends on intensity. How it is depending? Photocurrent actually depend on intensity like this. It varies linearly. Photocurrent depends on intensity. Intensity, this is photocurrent. So photocurrent. Okay, photocurrent depends linearly with intensity. If you increase the intensity, photocurrent will increase. Okay, but if you have frequency variation, actually frequency variation doesn't have any direct relation to the value of the current, but it has a relation with the maximum kinetic energy of the photon. So that is what we have seen. And see, stopping potential EV0 is actually exactly equal to the maximum kinetic energy of the electron, emitted electron. Okay, stopping potential is equal to the maximum kinetic energy of the emitted electron. Now you look this figure. This is photocurrent, this is anode potential, and these are the stopping potential. This is one stopping potential, suppose V01, and this is V02. Retarding potential, or retarding potential means you are just decreasing the potential, accelerating voltage. You are just applying opposite polarity of the potential, accelerating potential. That is why it is called retarding potential. And where the photocurrent is becoming zero, those are called stopping potential. So we can see there are two stopping potential. This is one, another one is this one. Okay. Now there are three curves. That means what? We have taken three different intensity and frequency. So here we have taken three different frequencies, not intensity, different frequencies. Three different frequencies. So which of the following statement is correct? Let us say curve 1 and curve 2 represent that incident radiations of same frequency but different intensities. So different intensities means their current, different saturation current will be different. So here 1 and 2. See 1 and 2, this is 1 and this is your 2. So they have different photocurrent. That means they have different saturation current. So intensities are different. That is true. Now let us see radiations of the same frequency. See, this stopping potential is directly proportional to frequency. If if the frequency of these two are same, then only they are going to become zero. The photocurrent going to become zero for these two radiations at the same stopping potential. Okay, at the same stopping potential. So since this curve 1 and 2, they have the same stopping potential, that means they have same frequencies but different intensity because they have different photocurrents. Saturation currents are different. Suppose this is I1, this is I2 and this is I1. So I1 has current, I1 has value less than I2. That means I2 has greater intensity. Okay, all right. So in this case, the first option is correct. Let us read the other options also. So curve 2 and 3. 2 this curve and 3 is this curve. So 2 and 3 represent that they have same frequencies and same intensities. They don't have same intensity. I'm sorry, they may have same intensity, but they don't have same frequency. See, they have same intensity because their current is same here. Okay, 2 and 3 have the same current, so they may have the same intensity. That is true, but they have different stopping potential, so they have different frequencies. So this is not correct. This is correct. Curve 2 and 3 represents that radiations have different frequencies. No, they have same frequencies and different intensity. No, they have, I'm sorry, they have different frequencies, true, but they have different intensity. That is not true. So that's why this is also not true. They have actually same intensity because their current value here is same. Saturation current is same, so intensity must be same for curve 2 and curve 3. But here they are saying that this is different. Now curve 1 and 2 represent that the incident radiation of different frequencies. 1 and 2. 1 and 2. Now no, this is not true because they have same stopping potential, so they must be having same frequency. Okay, so yeah, so this is how there are few more problems. These are already given in the quiz sheets in our site. Maybe you can go and check there. I'll just take up a final problem from de Broglie's hypothesis. Look, which of the following gives the correct expression for the thermal neutron? So for a thermal neutron at thermal equilibrium at temperature, okay, thermal. So this is actually for a thermal neutron in the heavy water. It is in thermal equilibrium at T Kelvin temperature. So which one is giving you the expression for expression for uh, correct expression for correct expression for de-Broglie de-Broglie's wavelength. Okay, de-Broglie wavelength. Okay, so de-Broglie's wavelength, we know lambda is equal to a by p. P is the momentum. So here momentum is not given. Rather, it is mentioned that this neutron is in thermal equilibrium. Is in thermal equilibrium at T Kelvin temperature. So from there we have to find out what is the momentum. So when a thermal neutron is in equilibrium with this much Kelvin temperature, we can say that it has kinetic energy, kinetic energy can be written as P square by Tm, which is equal to 3 by 2 K. K is the Boltzmann's constant. Okay, this is the thermal energy which is providing the kinetic energy to this neutron. Okay, at this particular temperature T Kelvin. So we can just find out P from here. What is that? So you will get 3 kT into m, 3 mkt under root that. Okay, so square root of that is P. So if you just put it here in this de Broglie relation, so you get de Broglie's wavelength as 3m, so h by under root 3m kt. So this is how you have to solve. So this is the correct answer. Okay. Okay, I'll stop it here with this, and thus we complete this chapter, radiation, dual nature of radiation and matter. In the next class, what we'll take the chapter atoms, and we'll see that we'll be applying whatever we have learned in the dual nature, like photons, concept of photons and energy of photons, etc. Those will be carrying forward those concepts to learn further in atomic physics. Okay, so Deepa, we- so do you understand whatever I have taught? Do you have any question query? Okay, if you don't have anything, I will stop it here for today. If you suppose get any questions on these topics, like these topics, whatever I have taught today, you can ask me any in any class. I'll be clearing your doubt there. Okay, so I'll stop it here for today. So bye for today then.